Okay, we're looking at the electromagnetism review. This first 14 or so, 15 or so are all matching. We've got our possible answer choices all up here, A through L. Let's start with number 1. If I'm going to decrease the number of loops on an electromagnet, what will happen to the strength? Well, there's a direct relation there, so that if I decrease the number of loops, then my strength of my electromagnet will also decrease. That is answer choice B. And the next one is step-down transformer, the number of coils blank and the voltage blank. So this is also a direct relationship. And this is a step-down transformer. And step-down means to reduce. So if I'm reducing the voltage, then I have to reduce the number of coils or decrease. And as a result, my voltage will also decrease. And a step-up transformer will actually do the opposite. So in order to increase the voltage, I have to increase the number of coils. It's a step-up transformer. Number 4, opposite poles of a magnet. Well, we know like poles repel, opposite poles attract. A phone charger uses a transformer to blank the voltage provided for the battery. Well, we've talked about this before, and there are about 110, 120 volts coming out of a wall outlet. Your phone cannot run off that much, so it has to be reduced. So the transformer, a step-down transformer, is going to decrease the voltage provided for your battery. Number 6 is the velocity of a particle increases. What happens to the force? Well, they are directly related, so that if my velocity speeds up, then my force is also going to increase. So as that current gets faster, then there's going to be more of an electromagnetic force. Number 7, the north pole of a compass points to Earth's magnetic south pole. South pole, which is letter I. Remember, the geographic north is magnetic south, and geographic south is magnetic north. So geographically and magnetically, they are flipped. They are opposites of each other. Number 8, an electron traveling into the page experiences a magnetic field pointing out of the page. What is true about the force? Well, we've talked about how there are 3 instances where there will be no force at all. And if we have a stationary charge, meaning it's not moving, a neutral charge, meaning it doesn't have any charge at all, or if the charge and the magnetic field are parallel. So here I've got an electron traveling into the page. So if you think 3-dimensional, I've got something traveling into my paper, and at the same time I've got a magnetic field that's pointing out of your paper. They are parallel to each other, and when they are parallel to each other, there will be no force, which is, whoops, I was about to write no force. No force is answer choice J. Okay, no force at all. They will be the strongest when the charge and the field are perpendicular to each other. Here they are parallel. Number 9, magnetic field lines point towards the blank end of the magnet. Well, we know that field lines come out of the north and into the south, which is letter I. Number 10, a motor converts blank energy into blank energy. So a motor will take electrical energy, like say from your car battery, and it generates or creates mechanical energy, moving parts, which is letter F. A generator does the exact opposite. So a generator is going to take those moving parts, and it's going to use those moving parts to create electrical energy. Number 14, if the south end of 2 magnets are pointing towards each other, the magnetic field lines would move blank from each other. Well, if they are 2 south ends, that means they are like poles, and we know that like poles will repel each other. They will move away. L. Number 15, if a student turns the handle of a generator 12 times and the motor turns 10 times, then the number of turns would blank if a light bulb was added. So first of all, we've talked about how we lose efficiency through resistance in the wire. There's friction going on. So we see here that I've got 12, I'm putting in 12 turns and only getting out 10 turns. Okay, so it's not 100% efficient. If I add a light bulb that's in series, remember, if I add a light bulb, I'm adding a speed bump, it's slowing down that current even more. I'm creating more resistance than it already has. So if I'm creating more resistance than it already has, then if I turn it 12 times, it's definitely going to turn less than 10 times. Okay, so the number of turns would definitely decrease. Answer choice B. Okay, now let's look into the math here. Number 16. Number 16 says a 3 centimeter long wire carries a 5 amp current. The wire is placed at right angles to the magnetic field of induction, 0.18 Tesla. What is the magnitude of the force? Okay, so what I'm solving for is force. I'm given the length of this wire is 3 centimeters. I'm given the current of this wire is 5 amps. And the magnetic field is 0.18. Now, looking at the units, Tesla measures magnetic field, amps measures current, newtons measures force, centimeters, yes, they are a unit of measure for length. However, the standard measurement is in meters, so we need to convert this to meters. So I know that there are 100 centimeters in 1 meter. So 3 divided by 100, or simply move the decimal place 2 spots to the left, gives me 0.03 meters as my length. Okay, so I'm solving for F, and I've got B, I, and L. So I'm not going to use F equals QVB. I'm going to use F equals B, I, L. So F is unknown. B is 0.18. I is 5. And L is our new conversion, which is 0.03. When I multiply all three of those together, you should get 0.027, and we're measuring force. My units are in newtons. So 0.027 newtons. Next page, let's see, number 17. In number 17, I've got a wire that's carrying a current of 2.5 amps, and it's perpendicular to a magnetic field with induction of 0.80 Tesla. The force on the wire is 0.04 newtons. I want to calculate the length. Okay, so let's see, I've got a current, which is 2.5. Whoops. This is I, perpendicular to a magnetic field, which is B. The force is F. I want to calculate the length, which is L. Okay, so I'm solving for L. There's only one equation with L, and it's F equals B I L. Here I have the force, which is 0.04. B is 0.80. I is 2.5. And L is unknown. Okay, so first step I'm going to do is I'm going to multiply these two, 0.80 times 2.5. And when I do that, I get 2, still multiplied by L. On the left, I got 0.04. My last step here is to divide by 2 on both sides. These cancel out. And when I take 0.04 and divide it by 2, I get 0.02 meters as my length. Okay, let me try to clear up some room here. Okay, number 18, if a proton with a charge of 1.6, so this is Q, moving at 5 times 10 to the 5th, this is V, and there's a uniform field within the gap. So 0.5 Tesla, Tesla measures magnetic field, which is B. I want to find the magnitude of the force, so I'm solving for F. So I've got Q, V, and B. Solving for F, there's only one equation I can use, and it's F equals QVB, where F is unknown. Q is 1.6 times 10 to the negative 19. V is 5 times 10 to the 5th. And B is 0.5. When I multiply Q times V times B, I get 4 times 10 to the negative 14 newtons. Okay, number 19. If a magnetic field produces a force of 3 times 10 to the 15th, so this is F, to the north on an electron with a charge, okay, so this is Q, moving to the east at a speed of 5 times 10 to the 6th meters per second, this is V. What is the strength of the magnetic field? So I'm solving for B. Okay, so got F, Q, and V. I'm solving for B. I'm going to use the same equation that I did up above, Q, V, B. This time, however, I know what F is, and F is 3E negative 15. Q is a negative 1.6 E negative 19. And V is 5 E 6. And I want to solve for B. So the first thing I'm going to do is I'm going to multiply these two together, Q and V. And when I do that, I get negative 8E negative 13. Negative 8E negative 13, still multiplied by B, equals 3E negative 15. So my last step here is to get B by itself, and to do that I have to take negative 8E negative 13 and divide it onto the other side. So I'm going to go ahead and clear up some space. Again, space is a little tight here, so I'm going to rewrite this. All right, so we had, let's see, we had 3E negative 15 divided by a negative 8E negative 13 equaled B. And when I divide those two, I get a negative 0.00375 Tesla as my magnetic field. Okay, looking at the next one, number 20. The primary side of a transformer. So we're dealing with a transformer here, and transformers can either increase or decrease voltage. It says the primary side has 250 volts, so this is V primary, and 100 turns, so this is primary turns. The secondary side has 5 turns, so this is my secondary turns. I want to figure out the secondary voltage, Vs. So using my equation, primary voltage divided by secondary voltage equals primary turns divided by secondary turns. My primary voltage is 250. My secondary voltage is unknown. My primary turns is 100. My secondary turns is 5. So my first step here is to cross multiply 250 times 5 and 100 times Vs. So 250 times 5 gives me 1250. And 100 times Vs gives me 100 Vs. Last step is to divide both sides by 100. So these cancel out. And 1,250 divided by 100 equals 12.5 volts. Okay, number 21, I've got the voltage up from an electric company is 10,000 volts, and it's stepped down, so it's being reduced to 220. So I've got a primary voltage, and I've got a secondary voltage. On the house's secondary coil, there are 1,000 turns of wire. So this is the secondary turns. And I want to know how many turns are on the electrical company's primary side. So I'm solving for NP. Alright, so my equation says that primary voltage over secondary voltage equals primary turns over secondary turns. So if I plug in what I know, my primary voltage is 10,000. My secondary voltage is 220. My primary turns is unknown. And my secondary turns is 1,000. Okay, so I've got a fraction on the right, fraction on the left. I'm going to cross multiply 10,000 times 1,000, and then 220 times n. So when I multiply 10,000 times 1,000, I get 10 million. And then 220 times n is 220 n. And my last step here is to get n by itself. So I'm going to divide both sides by 220. When I do that, these cancel out. And I'm left with 45,454.55 turns equals n. Okay, number 22. When is a permanent magnet magnetic? Well, this is your key. If it's permanent, it's always magnetic. When is an electromagnet magnetic? Well, these types of magnets can be turned on and off. So they're only magnetic when there is an electric supply. So whenever there's electricity provided, such from a battery or from a circuit, the wall outlet, only when electricity is provided. When there's no electricity provided, these types of magnets are not magnetic. Okay, for 24 through 31, we're going to go through and identify if the statement is true or false. If the statement is false, we're going to change it to make it true. So number 24 says, magnetic fields are two-dimensional only. That is a false statement because magnetic fields are three-dimensional. They surround the Earth. Okay, the Earth is spherical. The magnetic field is also spherical around that Earth. All right, 25. Electromagnetic force is inversely proportional to the magnetic field strength. That is also false because the electromagnetic force is directly proportional to the magnetic field strength. So as the force increases, the magnetic field increases. If the magnetic field decreases, the force also decreases. Number 26, field lines are closest at the poles and further apart near the middle. That is a true statement. You'll notice that the field lines converge at the poles, making them stronger at those points. Number 27, magnetic fields are strongest near the middle of the magnet. Well, that contradicts number 26, so this is false. Magnetic fields are strongest at the poles. Number 28, the Earth's magnetic field has never changed. That is also false because our core is made up of molten iron and it's continuously moving. The Earth's magnetic field has changed a few times over the Earth's lifespan. There is plenty of evidence to support this, so to make this true, we're just going to cross out never. Number 29, some animals can detect the Earth's magnetic field. That is true. Animals that migrate during the winter, such as birds, geese, they can detect the Earth's magnetic field and allows them to know where south is during the winter and north is during the summer. Number 30, the magnetosphere is actually formed by the magnetic field of the Earth and protect us from cosmic radiation. That is true. Without this magnetosphere, we would be exposed to harmful radiation, which could be very damaging to our DNA. Number 31, a changing magnetic field from the turning of a wind turbine generator will create direct current. That is false. If the wind turbine is creating a generator, then there's fluctuation going on. It's going back and forth. The magnetic field is alternating, which would create alternating current. Number 32, give 3 examples of electromagnets. There are some trains that run off magnetism. They're commonly referred to as bullet trains. They don't have any wheels. They just sort of levitate above the track due to that magnetic force. The junkyard cranes that you see maybe in a scrapyard, a metal scrapyard, can lift metal scraps at the push of a button and then release scraps wherever they need to be. The magnets that hold on to our doors in our hallways, you may or may not have noticed them, but during the fire drills, those magnets are cut off from electricity and they're no longer magnetic. And during a fire drill, you'll notice that the doors are all closed in the hallways. And one other one is simply a nail that's wrapped in electrified copper. So you saw this in our rotation lab, where we had a nail and copper wire, and the copper wire was wrapped around the nail several times. When we added it or connected to the battery source, that nail was able to pick up paper clips, making it magnetic. But as soon as I removed that power source, the magnetic properties went away. Number 33, identify 3 examples of electromagnetic induction that you saw in the induction lab. Well, in the induction lab, you saw a generator where we took mechanical energy and converted it to electrical energy. You saw a motor where we connected or converted electrical energy to mechanical energy. And you saw an electromagnet where we ran a current through some wires, inducing a magnetic field. And the last one, number 34, in order for a magnet to be at maximum strength, the domains, so we're talking about the arrangement of the atoms, the electrons within this atom, they all need to be aligned. They all need to be perfectly in rows. Heat and dropping these substances will misalign or create an uneven balance between all the domains, making them less magnetic.